I always forget this one. Okay. Now, do you have a question? Or just about the recording?
That was going to be my question. Sorry.
Okay. So again, I will repeat this again quickly. So this circuit has a two-stage CMOS amplifier. The two stages are...
Right, now you're not sharing the screen.
Your screen isn't
Oh,
showing.
sorry. Okay. Can you see the screen now?
Yes.
Yes, sir.
Okay. So this operation amplifier or differential amplifier has two stages. The first stage is a differential pair, consists of these two transistors. They are PMOS differential pair. Whenever you see a face-to-face transistor, two transistors with a tail like this connected in this from the source with a tail current, then we assume this is a differential pair. Okay, with two inputs as well. So we have two inputs, the plus and minus, the inverting and non-inverting. So this is the first stage in any operational amplifier, the differential pair. Okay, and these are PMOS differential pairs, so this is why it's upside down. The current comes from the top, not from the bottom, because this is PMOS. And this current mirror also, you know, the current source, the bias current source of this differential pair is not an ideal current. It comes from a current mirror. So this construction here is a current mirror that mirrors this reference current to this current I. So if Q8 and Q5 are exactly the same, which is the case in the example, by the way, I think in the example, the 9.6, you have Q5, Q7, Q8 exactly the same. So if you know I reference, which is given, I believe, 90 milliamperes, now you know I, and this I will be divided into two halves, one half through Q1 and one half through Q2. Okay, and Q1 and Q2 are loaded not with resistors, but with another current mirror. So this is another current mirror. It's an NMOS current mirror. So this is a PMOS current mirror. This is an NMOS current mirror. The only difference, you know, that the equation has the V threshold N and V threshold P. You know, it's the same equations, but you have to be careful with the polarity and the values. So the input comes from these two inputs. The output is taken from a single-ended. It's not taken differentially. So we don't take the V1 minus V2 or V2 minus V1. We take just one of them. And it's connected to the next stage, which is the common source amplifier. Why common source? Because the source here is connected to the minus VEE, which is AC ground. And the drain is connected to, instead of a load RD, we have a current source. You know, this is a part of the current mirror here, because this is a current mirror and the midpoint is also connected to this. So this is parallel to this, like if you assume Q5 and Q7 are parallel to each other. So the same current I will flow here. So we have a current here that's 90 microampere, I believe. The current here is also 90. The current here is 45. Here is 45. Here is 90. So now you have all the DC current in the circuit. From this DC current, you can calculate VGS. You remember the equation that links VGS and ID. So for each one, you can calculate V over drive and VGS. First, you calculate V over drive from the equation, and then from V over drive, you calculate VGS. Okay. Then you replace each transistor with its RO. Okay, and start to do the AC analysis, finding the gain and so on. Okay, so this is a very important example. Go ahead and study it. You might expect a question like this in the exam. Okay, so try to understand how to analyze this in DC and AC and everything. Okay, does anyone have any question about this example? Okay, so let's move to a new topic now, which is the active filters. Okay, so in this topic, we are going to talk about, first of all, introduction about active filters, ideal responses of filters, realistic or approximate or practical responses of filters. Then we will study the first order stage, then second order stage, and we will implement this using these 4 circuits: the Salenki filter, the Friends filter, the Thomas filter, and the KHN filter. So these are names of the inventors or those who initiated these circuits. So filters are very important in many applications, especially in communication systems. So we use filters as electrical and electronics engineers. We use it widely in many applications. The goal of a filter, as you understand, is to pass certain band of signals and to reject other bands, okay? We can implement filters using passive components, which has no active component like a transistor or op-amp. So passive components means just resistors, capacitors, and inductors. That's it, okay? And these passive components, they work great above the 1 megahertz range. So if you have a circuit tuned in high frequency, most likely you're not going to use active component like a transistor or op-amp, okay? Why is that? Okay, we'll go back to the frequency response that we covered a long time ago, because these devices have a limited frequency response, right? And most of them, they work fine up to 1 megahertz. Above that, you have the output stray capacitors or internal capacitors that will limit this frequency range. Of course, with the development of technology, we might have might see some active components that work in higher frequency. But in general, if you'd like to design filters in the high frequency above 1 megahertz, you usually use passive components only. So what's the difference between passive and active? Passive has no power gain, okay? They don't provide any power. They are not connected to the VCC or VDD or VEE and so on. So by having this kind of passive filters, it's difficult to tune. If you'd like to change the frequency to tune it from one center frequency to another, this is not easy. On the other hand, the active filters, which involves transistors, op-amps, these active components, they are built using resistors, capacitors as well as the active components like transistors and operational amplifiers. We might use inductors, but capacitors can do the job, the work by themselves. And they work, as I mentioned, below 1 megahertz, and they have a power gain and relatively easy to tune. So these are the differences between passive and active filters. So, as it's mentioned, filters can separate desired signals from the undesired signals. So if you have noise or interference, you can, and you know the band of this noise or interference, you can select your wanted signal and reject these noises and interferences. Okay. They are widely used in any application where you have speech processing, video processing, and so on. Okay. Well, before we see how to implement a realistic or a practical filter, we need to understand what the features and the characteristics of ideal responses are. Okay. So by frequency response, as you remember, we mentioned this many times, we mean that it's the voltage gain versus the frequency. If you plot h of omega versus omega, this is, of course, we cannot plot this in one plot because h of omega is a complex quantity. So we plot h of omega magnitude, and we call this magnitude response versus frequency. And we plot the phase of h of omega versus frequency, and we call this the phase response. So this is what you mean by the frequency response. Frequency response has two components: the magnitude response, which is h of omega magnitude versus omega, and the phase response, which is the phi of omega, or the angle of h of omega versus omega. In this course, we are not concerned about the phase. We're going to talk only about the magnitude response. So whenever we say frequency response, we mean the magnitude response. We don't care about the phase too much in this course or in this topic. We have 5 categories or 5 types of filters: low pass filter, high pass filter, band pass filter, band stop filter, and all pass filter. Okay, we're gonna explain them briefly right now. By ideal filter, we mean a filter that has unity gain in the pass band. So the pass band has a flat gain of 1, okay, which in decibel becomes 0 decibel. And that means we have 0 attenuation. So you don't have any attenuation in the pass band. On the other side, you have a 0 gain in the stop band, means that you have infinite attenuation. Okay. Also, you have a vertical transition. So the filter makes the transition from the pass band to the stop band in no frequency. So suddenly it goes from the pass band to the stop band. So there is no roll off. And finally, the phase shift is 0. This transistor doesn't make phase shift, or at least it makes a linear phase shift, okay? But ideally, we can assume that the phase shift is 0. When the phase shift is 0, that means that you have no delay, because phase shift produces delays, okay? However, these ideal characteristics are impossible to implement or to realize in real life, okay? Sometimes we call these ideal responses by the brick wall responses, because they look like a brick. If you see here, so these are the ideal responses. This is for the low pass filter, high pass filter, band pass filter, and band stop filter. You can see it has a flat, equal range of like pass band, which is 1, and 0 in the stop band. This is the low pass filter, 0, 1, here 0, 1, 0, here 1, 0, 1. So it's flat, and it has a sharp transition from the pass band region to the stop band region. These filters are impossible to realize in real life because of many reasons. First of all, you cannot have this sharp transition in all of a sudden like this. Second, if you implement this, this is gonna be, if you go back to the time domain of this filter, you will find what's the inverse Fourier transform of a square pulse. Do you know? If you have this as a frequency domain, this is h of omega, right? So this is h of omega, and h magnitude now it's the same as h of omega because the phase is 0, right? So this is h of omega. If you do inverse Laplace, inverse Fourier transform of this one, what do you get? Remember, a square pulse in the frequency domain. What's the inverse Fourier transform of a square pulse? Have you studied this in the signals and systems, or maybe algebra, or I mean like math, or? Okay. The inverse Fourier transform of a square pulse is the sinc function, okay? If you remember this from the signals and systems, if you inverse transform, get the inverse transform of this pulse, is going to give you sinc function. So sinc function goes like this. So let me just plot it here. So sinc function, if you do a time domain inverse Fourier transform, you'll get something like this. Okay, it's the sinc function, right? So this is h of t. Okay, versus t, of course. Okay, so what's wrong with this? What's wrong with this impulse response? Why cannot be implemented in real life? Well, as you can see, it goes to the infinity, from 0 to infinity in this side, and from 0 to minus infinity to this side. So it's infinite, it has infinite response, and it's not stable, it's unstable. Okay, first of all, it's unstable. Why? Because if you integrate h of t absolute value from minus infinity to infinity is not finite, it's infinite. So if h of t, if you integrate h of t absolute value from minus infinity to infinity, and it was not absolutely integrable, then the filter is unstable. Also, this filter has a negative part, like it happens at the negative time. And if you have a filter that happens in the negative time, that means it's a non-causal. Non-causal means it depends on the future. Okay, this part here, the negative part, depends on the future. And you cannot build a real-time application filter that depends on the future. Okay, so there are many things, that makes this impossible to be implemented in real life. So this is why we make the approximation, not the ideal response. Okay. Now we go to the approximation. So these are the approximated responses. Okay, so the ideal responses cannot be realized in real life in a practical circuit. So to build a practical filter, we have to compromise a little bit with these three regions. So they are approximated according to the specifications given, the given specification. So when someone gives you a specification about filter, he's not going to tell you, okay, I need the gain to be constant all the time until the cutoff frequency and then zero after that. No, he's going to tell you, okay, I need the gain to be within certain attenuation or gain, within certain gain. So the maximum gain should be 1 or 0 dB, and I accept to go below 0 dB to like 0.1 dB or something. And this can go until you reach certain frequency. We call it the passband edge. So this is the edge of the passband. I don't know if you see did you see the pointer or the mouse? This one here. Can everyone see it?
Yes.
Okay. So this edge here is the beginning of the end of the passband. So this is WP. We call it WP. Okay. So WP is the passband edge. Okay. In this case here we have two WPs, right? Because this is a low pass filter and this is a band pass filter. So in this one you have two edges here. This one edge and this one edge. So this is the beginning of the end of the passband, and this is the beginning of the passband. So this is WP1, WP2. Here we have only one because this is a low pass filter. Okay, and he will say also, I accept the attenuation to fluctuate, to have a stop band attenuation or stop band ripple within this range, or a stop band attenuation from the maximum with this amount. Okay, so he will leave some margin here. So this is the stop band gain. So he give you some stop band gain. I don't want like to have a zero gain, but I will accept some gain. Or that means I will accept some attenuation from this maximum with A max. So A max with A min. So A min is the stop band attenuation. A max here is the passband ripple, the tolerated ripple, to go below the maximum gain. And omega p is the corner or the edge of the passband region. And omega s is the beginning. So you can see that the transition doesn't happen in a sharp transition. It takes this delta omega to happen. The transition goes from omega p to omega s, okay? From the passband frequency, edge frequency to the stop band edge frequency, okay? And the transfer function of this filter is called h of s, and you substitute s. Remember how to go from h of s to h of omega? We said this before. You just substitute s with j omega, okay? If you substitute s with j omega in the transfer function, you will get the frequency. And if you take the magnitude of the frequency response, this is called the magnitude response or the gain. And if you take the angle of h of omega, this is called the phase response, but we're not going to talk about it. And if you take the magnitude and multiply it by 20, and take the log of the magnitude and multiply it by 20, you transform it into decibels. And if you take the negative 20 log the magnitude response, this gives you the attenuation, because attenuation is the reciprocal of the gain in absolute value, which means minus sign in the dB values. Okay, so this is a kind of realistic or approximated response. Okay. Okay, so next, we can implement these approximations using 5 famous methods. Okay, we can have these approximations to the ideal response using something called Butterworth approximation or Chebyshev approximation, inverse Chebyshev approximation, elliptic or Bessel approximation. Okay, we're going to see what do we mean by each one of them. Okay, actually each one has some advantages and disadvantages. We might sacrifice some characteristics or some features in favor of other features and characteristics. Okay, for example, we have a passband. You know, these are the main components in the filter. You have passband, you have stop band, and you have a transition, and you have, of course, a phase. So this the fourth one is the phase. So you have a passband, you have a stop band, you have a transition, and phase. Okay, so also if we add the phase as a parameter, if needed, then you can optimize the filter, each filter towards one of them. So someone would say, okay, I have no tolerance in the passband. Passband has to be flat as much as possible. Okay, so say, okay, we better go for the Butterworth. Someone would say, no, I need the stop band to be very low, very high attenuation in the stop band. We say, okay, we can go for maybe elliptic. Okay. Someone else might say, no, I cannot sacrifice the phase. The phase has to be linear as much as possible. I don't care about the passband too much, stop band, the transition band so much. We will tell him, okay, we can go for Bessel approximation. So it's a trade-off, okay? So let's see how to find these things and how to design them, okay? First of all, let's understand these approximations. So the Butterworth approximation, as you can see in this graph here, has this transfer function or this frequency response, the magnitude response. As you can see, it's flat all the way up to the corner frequency or the passband frequency edge frequency, and then it rolls off monotonically. Monotonically means it reduces all over the frequency. Okay, it cannot go up again. You know, it goes down, 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 down. It will never jump and fluctuate again. So it's flat, almost flat, then goes down by minus 20 dB per decade, 40 dB. It depends on how many poles we have. The order, so if you have an nth order, a second order, then this is going to be 40 dB per decade, minus 40 dB per decade. If we have first order, this is going to be only minus 20 dB per decade, and so on. So it's well known by its maximally flat. So maximally flat means in the passband, it's flat. It does not fluctuate. And it goes monotonically down by minus 20 n dB per decade in the stop band. Okay, and n is the order of the filter. The main advantage of the Butterworth approximation is its flatness. So if you ever interested in a filter that gives you a uniform gain in the passband, okay, which is flat, does not go up and down, no fluctuation, then you opt for Butterworth. Okay. The main disadvantage of this filter is the roll-off here. It's slow. It has a very slow roll-off. It makes the transition from the stop band to from the passband to the stop band very slow. Okay, so if you are interested in having a sudden sharp transition here, don't use the Butterworth approximation. The second one is Chebyshev type 1. We call it sometimes type 1. And as you can see, it has some ripple. You know, if you allow some ripple, opposite to this one doesn't have any ripple. You know, it's flat. If you allow some ripple in pass band or stop band, this will give you the benefit of going sharper. You know, the transition will be sharper. If you look at this transition and this transition, this one is slow transition or slow roll off. This one is a fast or sharp roll off. Okay, so this is the main advantage. You sacrifice a little bit with some error here. You know, like the gain here is not uniform. You accept some attenuation a little bit, but it's very small, like minus. You can go from 0 to minus 0.9 or something, or like minus 0.1 or something. And you gain, on the other hand, by doing this, you gain the sharper transition roll-off. Chebyshev type 1, or Chebyshev, we sometimes call Chebyshev, or type 1, has ripple in the pass band, but no ripple, as you can see. It's monotonically, you go like down, like similar to the Butterworth in the stop band. It does not go up again. So there is no fluctuation or no ripple in the stop band. You have a ripple in the pass band and you don't have any ripple in the stop band. Okay. The number of ripples, the number of ups and downs, the peaks and valleys here, it depends on the order of the filter. Okay. And actually, exactly, it is half of the filter order. So if you have an order 10, then you will have 5 peaks here. If you have order 4, then you will have 2 peaks and so on. Okay. The other one, you know, the other type of Chebyshev is the type 2, which sometimes we call it inverse Chebyshev. So inverse Chebyshev or type 2 is has the opposite. It's flat in the pass band and has ripples and attenuation, you know, fluctuating attenuation in the stop band. And again, you can see the roll off also in the transition band is similar to this one, you know, almost the same. You know, you have, but it's much better than the Butterworth. See the Butterworth? These are these plots are taken from different filters with the same order. So if you have a Butterworth filter with order, let's say, for example, actually you can tell here if you look how many decades, how many dBs per decade we dropped here, we can tell how much is the order here. So assume if this is 5/5 order, so this is a 5th order Butterworth, this is a 5th order Chebyshev, and this is a 5th order Butterworth with the same specs, you know, the same corner frequency for all. So to be able to compare them. So if you have the same order, you will find the roll off here is much slower compared to these two. Okay. Yeah, so in the Chebyshev, inverse Chebyshev, you will find certain points when you have deep notches like this in the stop band. It doesn't it does not matter too much because you're already attenuating. You are already attenuating everything in the stop band by at least how much here? At least minus 60 dB, right? So the attenuation here, it's minus 60 dB, and minus 60 dB is a really huge number. If you'd like to know how much is this, take the inverse slope. Okay, so but some frequencies have even deeper and more attenuation than 60 dB. Like for example, this frequency here. This frequency, the gain goes also up to almost 0. No, like it's minus 100 or below that, because that this filter has many poles very close to the imaginary axis. Okay. So we're not going to talk about these poles and zeros things, but in general. Okay, so the most important part in comparing the inverse Chebyshev with the other ones, it has a flat pass band and rippled stop band. Okay, the fourth one is the elliptic. Okay, now as you see from the Chebyshev, if you allow for a ripple, whether in the stop band or the pass band, you gain higher or faster transition. Okay, now how about if we do the ripple in both? And this brings us to the elliptic approximation. So elliptic, filter has ripple in the passband and the stopband at the same time. So imagine that transition will be sharper and sharper. Okay, and by utilizing something like this, you might have almost the same response compared to the other with lower order. Okay, and if you have the same order, you might have like much sharper transition response compared to the others. Okay, but with an expense. This doesn't come for free, actually. Okay, so what's the expense here? The major disadvantage of this filter is the nonlinear phase. If you look at the phase of this one, but it's not shown here, if you plot the phase against the frequency, the phase is highly nonlinear. So if you are okay about the nonlinearity of the phase, which is not all the applications appreciate this, some applications maybe in communications or speech processing or something or whatever, it's not appreciated to have a nonlinear, and we need to have linear phase. Okay, so if you don't care about the phase too much and you need the sharpest transition like this, opt for the elliptic filter. Why? Because it has a ripple. It gives you a ripple in the passband and ripple in the stopband. So this makes the transition much sharper compared to the previous one. Now, if you care too much about the phase, not about the gain, then you have to go with the Bissell. And if you can see, Bissell here is not flat too much in the passband, and the roll-off is horrible. It's a very slow, and even slower than the Butterworth. Okay, but if you look at the phase response of this filter, it's almost linear. Okay, and also the other disadvantage is this filter has the highest order or greatest circuit complexity of all approximations. Okay, so this is just a quick comparison between these 5 approximations. We cannot, as I mentioned, we cannot build a filter with a flat, 100% flat passband, even this one or this one. Okay, the Butterworth. The Butterworth is not 100% flat. It goes, gradually lower, because this is a dB log scale plot. You don't see the the rolling off of the passband, but it actually goes down. Okay, but it's much flatter than these ones. So you cannot build one with a flat passband and a zero stopband and a sharp transition. This is impossible to be implemented. Rather than doing this, we do the approximation using either Butterworth approximation, which is called maximally flat, Chebyshev type 1, which has a ripple in the passband, no ripple in the stopband, inverse Chebyshev or Chebyshev type 2, which has a flat passband and a rippled stopband, or elliptic approximation, which has ripples in both passband and stopband, or you can opt for Bissell approximation, which has a much linear phase shift compared to the others. Okay. Okay, now we can see this is another example of these filters in the passband filter, the bandpass filter. Okay, so these examples are low-pass filters, and these are examples of bandpass filters. So you can see this is the bandpass Butterworth. This is the bandpass Chebyshev type 1. This is the bandpass Chebyshev type 2, and this is the bandpass elliptic, and this is the bandpass Bissell approximation. You can understand, this is flat here and go monotonically like this, and it does not have ripples anywhere. This has ripple in the passband, no ripple in the stopband. This is flat here and ripple in the stopband. This has ripple in both. This has no ripple, but again, it's not flat in the passband. So just to increase the linearity of the phase shift. Okay, so this is a comparison between the 5 types. As I mentioned, with the passband, stopband, and the transition. And also based on the linearity, the phase linearity, we can represent it by step response. If you have the input as a step function, so if the input was a step function like this, if you have a linear phase, okay, the output will be closer to the step function. If you have nonlinear phase, the output will not be very close to the step function. So we can see the best one among them is the Bessel because it has a linear phase. Okay, other ones, the worst among them is elliptic. Why? Because it has a very highly nonlinear phase response. Okay. You can use any op-amp circuit, as we're gonna see, to build any of these 5 approximations. We're gonna see now. Many different circuits are available to offer a trade-off between the complexity of design, sensitivity of the components, and ease of tuning. These are the 3 major points that we compare circuits with. Is the circuit complex? Does it have many components, many operational amplifiers, or just 1 or 2 or whatever? Second, the sensitivity of the components. Like if you design the circuit to be tuned at certain frequency, if you change one component, like if you go and buy the resistor and the design says 1 kilo ohm resistor, and if you go to buy this resistor and you find it 1.1 or 1.01, how much this error in the component will affect the frequency of the filter. Okay. The third point, is it easy to tune? Like if you design a filter at 1 kilohertz, and I told you, okay, no, I'm sorry, my calculations were wrong, and I need to retune it at 2 kilohertz. Is it easy? Just you replace one resistor or one capacitor with another value and that's it? Or you need to change the whole design? So these are the 3 parameters or points that you evaluate the goodness of a filter design based on them. Okay. For example, some second order circuits, and we're gonna here study first order and second order only. Why? Because higher orders, you can build them using first and second order. Like if you'd like to build a filter that's third order, you cascade second order with a first order. If you'd like to build a 6th order, you cascade 3 second order filters, and so on. So the building blocks of any filter are the first order and second order filters that we are going to study in these slides. So some second order circuits use only one op-amp, okay, as we're going to see, while others, and some other few components, of course, like resistors and capacitors, and others use 2 or 3 op-amps. So these others are more complex compared to the first one. Despite they have this simple circuit, they have a cutoff frequency that's heavily dependent on the component, as I mentioned. You know, they are simple in the circuit, so you have to compromise between the simplicity or complexity of the circuit and the sensitivity to the component. So the circuit might be simple, but it's very sensitive to the variations or the error in the component. Okay, and so on. Some other circuits, they need more op-amps, but they are easy to tune or less dependent on the component variation and so on. So this is what we're gonna see now. Any questions so far? Okay. I'm not sure if no questions is a good news or bad news. Okay. So if you have any questions at any time, just raise your hand and ask the question. Okay. Okay, now let's, as I mentioned, the building blocks of any active filter are any filter, the first order stage and the second order stage. So first we study the first order, which is easy. So we can see how to do the analysis. And what I need from you, okay, in all this, you know, and this is something you have to expect in the exam, is to find the transfer function and the frequency response, okay? How to find it. Whether I give you first order, second order, and I will show you examples now. So it's very important to go through any circuit and try to find the frequency response, okay? Or at least the transfer function. Okay, so first order, by first order we mean one pole, okay? And take it as a rule of thumb now in this, in these slides, that the order of the filter, of the active filter, is determined by the number of poles, and it's determined by the number of capacitors in the circuit. So when I say first order, you should expect first order active filter. I'm talking about active. I'm not talking about passive filters, because passive filters have inductors. Okay, here we're not going to have inductors here. When I talk about active filters, so they consist of operation amplifiers, capacitors, and resistors. That's it. Okay. So when I say first order or second order or third order, that means this is the same number of poles you have, which is the same number of capacitors you have in the circuit. So this is the first order, so you should expect only one capacitor in the circuit. Okay. So have one capacitor. If you have one capacitor, just one capacitor, then there is no way to create high band pass filter or band stop filter or whatever. Okay. And by the way, when you go back, when we studied the types of filters, even the ideal ones, we didn't mention about the all pass filter. Okay. So we studied a low pass, high pass, band pass, and band stop. How about all pass filter? Why do we need an all pass filter? Does anyone know why do we need an all pass filter? We understand that we can use a low pass filter, high pass filter, band pass, band stop to reject some kind of frequencies and pass the others. But how about all pass filter? All pass filter is a flat, it's a flat line all the way from 0 to infinity. Why do we need something like this?
Yeah, I was going to ask that at the start of the class. Is it because of like trying to provide a gain to the whole thing?
No, what's the point if you make a gain of 1 or 2 or 10 to everything? This is just a constant. This is not a filter. We cannot call it a filter. If you provide a constant gain for all frequencies, this is just an amplifier. You just build an amplifier with inverting or non-inverting amplifier with 2 resistors, and that's it. Why we call it a filter in the beginning?
Because it filters out noise or something?
No.
What about phase?
Yes, yes, this is the answer. The all-pass filter doesn't care about the gain response. The gain is flat. The all-pass filter has a gain that's flat. But the phase is not linear, or the phase might be like something like this. So you compensate the phase. You build this filter to equalize the phase. You need like a phase shift here plus 90 degrees and here minus 90 degrees in this band of frequency. So you design an all-pass filter to change the phase response, to affect the phase, not the gain. Okay. So this is the main application of an all-pass filter, is to I don't say filter the phase, but to change or to alter the phase of the signal, to do something to the phase of the signal at certain frequencies, different than the phase in other frequencies. Okay. So now we cannot design a band pass filter, band stop filter, with just single order, because single order will make one pole, right? One pole that makes one corner frequency. So if you go back here, see, this one has 2 corner frequencies. You cannot do it with one capacitor, right? Because it has 2 poles here. If you have 2 corner frequencies, then you have 2 poles. So band pass filter need at least second order. Okay, but first order you can use it to do low pass filter or high pass filter. Why? Because low pass filter and high pass filters, they have 1 corner frequency. This is 1 here and 1 here. But this one, we have 2 corner frequencies. Okay. Okay, so how to design a first order filter? Well, let's look at this structure here. We have a non-inverting case. Why non-inverting? Because the input signal is connected to the positive terminal, while the negative terminal is either connected in a feedback of 1, okay, and this is a unity feedback, or through a feedback beta, which is R1 divided by R1 plus R2. Okay, so let's analyze these circuits and find the H of S. And again, I will repeat this many times in this lecture to show you how to find H of S. This is very important. You should be able, if I give you a circuit with a second order or first order for any structure, you will be able to find H of S. How to find H of S? Simply, we replace every component with its equivalent in the complex domain, in the S domain. So R in the S domain stays as R. C in the S domain becomes
1 over SC.
1 over SC. That's it. And you do the KVL, KCL, and you are done. Okay. Your goal is to find V output of S as divided by V input of S. And I think we did this before, and we're going to repeat it here again. So if you do KCL at this point here, at the V plus node, we call this V plus, and you have to remember two golden rules, okay? The first one is that these two voltages are the same, and there is no current getting into the amplifier. These are the two golden rules for the operation amplifier. Okay, so the gain here, K of the amplifier is 1, and the gain for the amplifier, the operation amplifier here is 1 plus R2 over R1 as we studied in electronics 1. So if you do KCL at this point, okay, so we call this V plus because it's connected to the plus, the V plus, and this is Vn and this is V out, okay. Now, since V plus is connected to V minus, in this case, V plus is the same as V out, right? Because these are virtually shorted, virtually, okay? They are not physically connected to each other, but virtually shorted. So if you have V out here connected through these two resistors to have V minus as V out times R1 over R1 plus R2, then V plus is the same as this amount, okay? So we call it K, you know, like V plus is K times V out. Sorry, 1 over K, because 1 over K is the beta, okay? So 1 over K times V out. So V plus is 1 over K times V out. So V plus, to find the current, to make KCL, we have two currents, one current here and one current here. The current through the R is V plus minus Vn over R, which is this one here. And the current here is V plus minus 0 divided by 1 over SC, which is this one here, okay? So you just separate the variables V plus and Vn and rearrange the equation. You come up with this one, and you multiply by 1 over CR in both sides, so you get this one. And you define 1 over CR as omega naught, which is the corner frequency, the 3 decibel frequency. So you end up with omega 0 or omega naught divided by S plus omega naught, where omega naught is this value. Okay. Now we don't need the transfer function between V plus and Vn. We need it from V out to the Vn. So we know that V plus is the same as V minus. This is rule number 1. And V minus is either the same as V out or V out times R1 multiplied by R1 divided by R1 plus R2, which is 1 over K, right? So V minus is V out over K. So if you substitute this one here in this equation, you end up with V out of S divided by Vn of S. And we're going to omit this S later on. Equals K times omega 0 over S plus omega 0. So this is the transfer function of a single order low pass filter, okay? And this case is called non-inverting case. Let's go to the inverting one. We can connect the inverting low pass filter this way. So you have 2 resistors and 1 capacitor. So you see the difference. This one has fewer components a little bit, but this one works as well. So we have R1, R2, C1, and again, K, when you have a low frequency, because this is a low pass filter, the gain will be minus R2 over R1. Why? Because in low frequency, this is open circuit, so this is gone. So you end up with R2 feedback and R1, and this is a negative or an inverting amplifier, so the gain in the low frequency is minus R2 over R1. And again, we do the KCL at this node. Now, in this case, V minus is the same as V plus. Since V plus is ground, then V minus is also a ground, and we call it virtual ground in this case. So we assume V minus is 0, and we do KCL at this node. So we have how many currents? We have 1, 2, 3. So the first one here is V minus Vn over R1, and this one V minus minus V out over R2, and also V minus V out over C1, or you can say V minus V out over R2 parallel to ZC1, okay, which is 1 over SC1, which is, and this equals 0. Now we understand that according to the golden rule of the operation amplifier, that V minus equals V plus equals 0. So you substitute this with 0, this with 0, and you solve for V out over Vn. This is what you get, and you just rearrange the parameters, and you get K times 1 over C1 R2 over S plus 1 over C1 R2. If you define 1 over R2 C1 as omega 0, then this will be exactly the same as the previous one. H of S equals constant omega 0 over S plus omega 0. But the K here is different than the previous one. The K here is given by minus R2 over R1 because this is an inverting amplifier. Okay. Since this one, if you plot the frequency response of this filter, you remember how it looks like? If you substitute S with J omega in this equation, you remove every S and you substitute J omega, you're gonna plot H of omega, right? And if you plot the magnitude, it's gonna be like this. It's gonna go flat and then make 3 decibel frequency and then go minus 20 dB per decade, right? So this is omega naught here. So this is omega naught. And this is 0 dB, right? And this one folds off with minus 20 dB per decade. Okay. So this is the feature or the characteristic of a Butterworth filter. So you cannot do any other filter, active filter or approximation except the Butterworth approximation. You cannot have ripple here. You cannot do, because having ripples here or ripple in the stop band needs a higher order filter, and a higher order filter needs more capacitors. Okay, so this is why we can only make a Butterworth approximation using first order filter. Okay. Okay, let's redesign the circuit again for a high pass filter with the 3 cases. So we'll talk about inverting without gain, non-inverting without gain, non-inverting with gain, and inverting. So this is how to do high pass filter using a first order high pass filter. Okay, so let's analyze, for example, this one. So if you do the same thing, you reach this transfer function. H of S is V out over Vn. It's going to be K times S over S plus omega naught, where omega naught is 1 over Rc and K is 1 plus R2 over R1. This is, I'm talking here about the non-inverting case. And if the inverting case, K is gonna be minus C1 over C2, and the omega naught will be 1 over R1 C2. And here, despite the fact that it's as first order, but you have 2 capacitors. Okay, if you go ahead, and I encourage you to go ahead and do the same analysis as we did here for these 3 circuits. Okay, you will end up with this one. So take this as an exercise at home and try to find H of S and put it in this form. Okay, so for the first order low pass filter, it's K times omega naught over S plus omega naught. For the high pass filter, it's K times S divided by S plus omega naught. So the difference here is this is an S, and here this is an omega naught. So just by switching from omega naught to S, this becomes a high pass filter, not a low pass filter. Okay, so you have a 0 here, right? At the origin. So this is how to implement a high pass filter, a single order high pass filter, and low pass filter. Let's take some examples. So let's assume this circuit. This is a non-inverting single order low pass filter. Okay. And by the way, you can tell directly from the circuit, or once you build and find the transfer function, you can tell whether it's a low pass filter or not. So also this might be a question, like I gave you a circuit like this and I ask you to find the transfer function. After you find the transfer function and I ask you some questions, what type of filter is this? What approximation? Is it Butterworth or whatever? And what is the cutoff frequency, for example? What's omega naught? Okay. And how to design, for example, or and so on. So let's analyze. This is an analysis example. So we are given the circuit with the components, and we'd like to find the output or the transfer function and the frequency response of it. Okay, so this is a low pass filter, and easily we can find H of S to be K omega naught over S plus omega naught, where K is 1 plus R2 over R1, as we did before. So this is, if you calculate K, is going to be 40. So the gain is 40. And the frequency omega 0, as we mentioned before, it's going to be 1 over R3 C1. It happens that this R is 3 now, it's not R, so R1. It's 1 over R3 C1. And if you'd like to find it in hertz, you have to divide this by 2 pi. So this is going to be 19.5 kilohertz. Okay, so this type of filter is a non-inverting because of this plus sign. First order low pass filter. Why? Because it's in this form. If you find this form at the end, you assume that this is a low pass filter. And if you plot the frequency response, if you substitute every S with j omega here, okay, and you plot this as magnitude, this is what you get. Okay, you will get a flat passband gain at 20 log 40, right? 20 log 40. If you calculate this by the calculator, 20 log 40. So this value here is K in dBs. Okay, if you convert K in dB, it's going to be about slightly above the 30 dB. And the corner frequency here should be how much? This should be this one here. Okay, I'm not sure this is, yeah, this is F in hertz. So this is going to be this one here. Okay. So this frequency is this one here. And how much this decay? It's minus 20 dB per decade. Okay. Okay, so this is an example of a first order filter, low pass filter. Let's take another example of a high pass filter. The same thing. So again, you might be given this circuit and not given this transfer function, and I ask you to find the transfer function. Don't say, okay, I memorize it, it's H of S, blah, blah, blah. No, you have to derive it from the beginning. You do KCL and you do these things until you find H of S, right? Okay, so from the previous analysis, we found that H of S is K times omega 0 over S plus omega 0. And this is, this is a low pass filter as well, but this is inverting one. Okay, and K here is minus R2 over R1, which is this value here. So this value here, but in dB is this value. Okay, you convert it into dB. And again, the negative you should remove this negative when you take the dB, because there's no dB for a negative number. This should appear in the phase. Okay, phase response. And the frequency is the corner frequency here. Okay. So this is again another example of a low pass filter using an inverting amplifier. Okay, now we move to the second order. Before we move to the second order, Does anyone have a question? Any questions?
So what does the K stand for again?
K is the gain of the operational amplifier at low frequency. If this is a low pass filter.
Okay, so
Okay. This is a good question.
In this example, you have a capacitor. You don't do anything with it.
No, at low frequency, this capacitor is open circuit, right? At this range of frequencies here, this range of frequencies, in this vicinity here, in this range here, when you have a flat top pass band, the capacitor is infinity, right? It's open circuit.
Yeah.
And if the capacitor is open circuit because the frequency is very low, why the capacitor is open circuit? Because the capacitance is 1 over j omega c, right? Which is SC, right? So when omega is very small, the whole value is very large. So the capacitor is open circuit. So we just remove it, okay? So you will have the gain as minus R2 over R1.
Oh, okay.
Okay.
So if it was a high pass filter,
Yeah.
it would have stayed there.
If it's a high pass filter, you go the other way around.
You cancel
Okay.
the loop.
The high pass filter, yeah, the high pass filter in high frequency, you have this impedance divided by this impedance.
Oh, okay. I see.
Right? And
Yeah.
this impedance is 1 over SC2, and this impedance is 1 over SC1. If you divide them, you get C1 over C2. You cancel the S's, and you get C1 over C2, because this is 1 over SC2, and this is 1 over SC1. If you divide them, you get it. So this one, this gain, where is this gain? Not at low frequency, this is at high frequency. Okay? So if you plot the high frequency, it will be like this. If you plot the frequency response of this one, and I encourage you to do this in MATLAB as well, to see. So it's gonna be like this. Right? This value here, you know, the highest value here is this value, is the K.
Oh, okay.
So this is the gain at high frequency, not at low frequency. In the low pass filter case, the K is at low frequencies. Okay. Yeah, this is a good question. Thank you. Any other questions? Okay, now we look at the design of a second order. As I said, to make higher order filters, you need to cascade second and first order. Okay, if you need 7th order filter, you cascade 3 second order with one first order. So we learned how to do the first order filter. Now we are going to learn how to design and implement second order stage. Before that, we need to see how the frequency response of a second order filter look like. Actually, this is not h of s magnitude, this is h of omega. We don't plot h of s, this is h of omega. Because it's a function of omega, right? Magnitude. How to get h of omega from h of s? We substitute every s with j omega. Okay. The second order filter looks almost the same as the first order, except with 2 important things. The first important thing is the decay, instead of having minus 20 dB, since this is a second order, is going to be minus 40 dB per decay. This is number 1. So the decay here is no longer minus 20 dB, it's going to be minus 40 dB. The roll off. The second thing is that it might encounter or might exhibit a notch here. You know, it might go smoothly to the stop band like this, or might make a jump before it goes. We call this resonance. Okay, we call it resonance. At the frequency at which this happens, it's called resonance frequency. Actually, it's not omega 0, it's slightly below omega 0. Call this omega resonance. So this is a feature that happens, that the filter can exhibit this peak before it rolls off. Whether we like this peak or not, whether it's desired or not, most likely it's not desired. If you are designing a low pass filter, it depends on the design. If you design a low pass filter, definitely you don't need this. This is a bad thing. But imagine if you are designing a narrow band pass filter. Your goal is not to design a low pass filter, but actually in reality, you would like to design a notch filter or a high quality band pass filter around omega 0. Well, you might need this notch, okay? So, for example, you can make your design like this. Go flat, and then go high up, and then go down like this. Of course, this is not a low-pass filter for sure. This is a band-pass filter, a high-quality band-pass filter that passes the frequencies in this band, which is these frequencies, and reject the frequency here and reject the frequency here. Because at this band of frequencies, the gain is very high, while below and above, the gain is very low. Of course, the gain, is not symmetric below and above, but it's much lower than the gain at this frequency. So actually, here you are designing a high quality. This is why Q is called the quality factor. So if you mean to design a high quality bandpass filter, you can do it with the high Q. So you increase Q maybe to 10 or 20 or 25, a very high Q. But if you mean to design, because as Q goes up, you see this notch here or this height goes up. As Q goes down or below or low, this notch or this height goes down, down, down until you reach the minimum here, which is the maximally flat, which is the Butterworth, is when Q, okay, so if Q is 1 over square root of 2, this is Butterworth. So that means you are designing a Butterworth approximation, okay? There's no peak or no height here, it's flat and it's smoothly going to the transition period, the region, okay? So second order filter has these two unique things. It has a Q factor that associated with it that makes the peak occur here, and a roll-off occurs at minus 40 dB per decade instead of 20 dB per decade, okay? The general form of any second order filter, whether it's low pass, high pass, or band pass, or all pass, this is the general form. It's a second order filter. So it has a polynomial of a second order in S in the numerator and a second order polynomial in the denominator, okay? And the coefficients here, we call them A2, A1, A0, or whatever the names are. And the coefficients here, this coefficient here must be 1, okay? So you have to have 1 here. If you don't have 1 here, you have to divide by this one, okay? So always we keep the coefficient of the highest order in the denominator as 1. If you have 4 or 5, you have to divide the whole equation, of course, numerator and denominator by 4 to get rid of it, okay? And the coefficient of the S parameter is called omega 0 over Q. Omega 0 is the corner frequency and the cutoff frequency, and Q is the quality factor, okay? And this is omega 0 squared. So this is a general normalized, if you can say, or standardized, so this is the standard form of a second order filter. So if you'd like to design one, you can determine omega 0 and Q by the pole location in the S plane, okay? Because poles are getting from the denominator, not the numerator. Numerator has zeros, right? This one has zeros, gives you the zeros. And this one gives you the poles. So the roots of the denominator gives you the location of the poles. The roots of the zeros of the numerator gives you the zeros. So if you find the roots of this equation, that means you find the location of the poles, you can bring them back and do the inverse of this function to get omega 0 and q. Okay, for example, if I give you two poles, one here and one here. Okay, so that means this is P1 and this is P2. So that means in the denominator, what do you have? You have S minus P1, because this is the first factor, and the second factor will be S minus P2. And if you multiply this factor, if you expand these two factors, you're going to get this polynomial, right? From the values, so B1 is given, B2 is given, right? So if you know these values and you expand this one, you're going to get this polynomial. Once you get this polynomial, look at the coefficient of S. This is omega 0 over Q. Look at the coefficient, the free term coefficient. This is omega 0 squared. So you first find this one and take the square root of it and substitute this one to this one, you get Q. So you can define Q and omega naught by just knowing the location of the poles in the S plane. Okay. How about the coefficients A2, A1, A0? These are determined by the zeros location, right? Because these are the numerator roots of coefficients. Okay. So the second point or the next point, depending on how the numerator is chosen, how these coefficients, so some of these coefficients might be zero. For example, if A1 and A2 both are zeros, this is a low pass filter. If A0 and A2 are zero, this is a high pass filter, and so on. We're going to see this in details now. Okay, I will finish this slide and we'll stop here. These values determine whether you have a low pass filter, high pass filter, band pass filter, and so on. Okay, as I mentioned, often two of them are zeros, and the other one is exists. So you know whether you have a low pass filter, high pass filter, band pass filter, and so on. You don't need to memorize each one, like the one that comes here next. You don't need to memorize all this, but you need to know at least some of them, okay, and you can substitute, okay. If you have this one, for example, how to know that this is a low pass filter? Well, you substitute S, very large S, okay. So when S is very large, that means F is very large, because S is j omega, right, and omega is 2 pi F. When you substitute S with infinity here, what do you get? So this is infinity square, infinity, so this is something over infinity, so this is zero. So at high frequency, the magnitude response is zero. So this is low pass filter. Here, or if you do this, if you substitute S with high frequency, with high value, you have to cancel and you divide by S squared first, and this is gonna give you a value, okay? So that means this is a high pass filter and so on. So you don't need to memorize them, but you need to substitute, and with S equals zero, S is infinity, and you see how the performance goes. We will study these four implementations of the 5 approximations. A filter called Salenky, or voltage controlled voltage source. This is an alternative name. Friends, you know, these are the names of the people who invented these filters, and these are the common names or alternative names. So Salenky, or voltage controlled voltage source, Friends, or multiple feedback filter, Joe Thomas, or multiple op-amp biquads, KHN. These are the first letters of the names of the 3 people who invented this, and the other name, alternative name, is the state variable. Okay, so we're gonna start doing this next time. Do you have any questions?
Could I please ask a question regarding the lab?
Sure.
So we had to submit the pre-lab today.
Yeah, just modify it according to the file. You know, I think it's easy to build the LabVIEW file I sent you, right?
Yes. The LabVIEW file, I and a couple of other students have already done it and also submitted it.
Mm-hmm.
The question I want to ask is the actual lab report due today also?
Yes. Do you have a problem submitting it today?
sort of, but okay. Okay.
Yeah.
You need like a few days extension or like
If,
that.
if possible, yes, sir, please.
Okay, that's fine.
What lab will we be working on today?
Today I'm gonna post, like just in like in 1 hour, 2 hours, the new lab. The new labs that we're gonna have. We're gonna do the theoretical part as the pre-lab and the multi-sim as the real lab. So I will post it today, and we're gonna work through it like in the lab time in the multi-sim. So please make sure that you have multi-sim ready in your device, and we're gonna work in the pre-lab if you want the theoretical part, and slightly with the multi-sim, and then next week we can finish if you have not finished it yet, and then we submit the lab report. Okay, we try to do like in 1 week. It's not gonna be difficult.
Okay.
So we'll try to start today, and next week we can finish it or start with the new lab. So we'll see. But I will post it today. It's about differential pair, differential amplifier.
All right, sir. Thank you.
Okay, so it will be covered the same material that we covered before. And the next one will be active filters, and the last one will be oscillators according to the lectures. We'll be having oscillators. Okay. The last one thing, as I mentioned at the beginning, I'm thinking of having a third quiz to improve your marks a little bit. So, but this has to be done outside the class time. So think altogether of a good time that you can apply for all of you. Like all of you are free. Even the evening, that's not a problem. Like if you have if you decide on time, like after hours, that's fine. Like 5, 6 p.m. that's fine. For 1 hour to have a quiz 3, we can have it before or after quiz 2. And I will take the highest marks, 2 marks of quiz 1, 2, and 3. Okay. So just think.
So we have to be live when we're taking it, or
yeah, we would like to practice the final exam. So you need to have a webcam, just focused on your face, just to see your face. It's also good to have a scanner, next to you. Like if you don't have scanner, that's fine. You can scan with your mobile or your cell phone, but try to find an application that makes good scanning, because most of the assignments you submit, I have hard time to follow, and read it sometimes because of the scanning, or the image that you take with your phone is not clear enough. So try to have a scanner. If you don't have a scanner, just make a scan with your phone, but using a software, not just taking a picture and upload. If you couldn't download anything and you take a picture, make it a nice picture and then add them up in one file, convert it to PDF, and then send it to me. Try to know how to convert things to PDF. Like I think you can put them in a Word file and then convert this Word file to PDF. It's easy, right? Or convert them. But you have to, don't send me 10 image files. Put them in one file, a nice format, nice resolution, and send it to me. Okay. So the questions will be online on Canvas. You answer them, maybe multiple choice or fill in the blank or something. But at the end, you have to also scan the work paper, the calculations, and send it to me, so that you don't be penalized if you have the final answer is wrong, but you did some work. You should get some marks for this. Okay, so think about a day and a time for the quiz 3, whether before quiz 2. We have quiz 2 on April 9th. So it's going to be next Thursday, not this week, the week after. So think of a quiz 3 time, either before quiz 2 or quiz or after, and let me know the day and time. Someone send me an email and let me know the day and time.
What's the next quiz about?
The next quiz will be mainly about the differential amplifier, the multi-stage, and the differential the operation amplifier, the differential pair.
So going over right now?
Sorry?
Today?
No, today's lecture we can involve it. It depends, like let's make it just on the differential pairs and multi-stage amplifiers. So the previous part.
Okay.
Okay. I'm gonna also post problem sets, and I might make an online tutorial, and I will record the file for some solved problems, and I will post it on the website so that you can, you know, see how problems are solved in this chapter, and we'll make it just for this chapter, you know, the previous one. But the quiz 2, I would suggest, the quiz 3, sorry, I would suggest having it on the active filters. So this is why I prefer to have it after quiz 2, not before. Yes, Arwasafi. You have a question? Okay. If no more questions, that's fine. I will see you again today at 2 p.m. Before that, I will post the new lab. And we can give this final lab of today's lab, of the previous lab, we can extend the deadline 2 days is okay, like to Thursday. Or I will make it Friday, that's fine. Make it Friday, midnight, okay?
Okay.
For the previous lab. And for this one, try to finish it in 1 week so that we finish early. And by the way, the lab, we need to have a final exam, okay? For the final exam, it's a simulation. I'm gonna give you one of the circuits in the previous labs and ask you to do some measurements on the multisim, okay? Calculations and measurements. So there will be a final lab exam on, I think, April 28th, okay? But it's going to be all simulation. So you need to have multi-sim working on your device, and you will select randomly a circuit and try to implement it and take measurements and send it to me. Okay?
All right.
Okay. Thank you so much, and see you soon.